what happened on class on Wednesday, and I'll post it, but it just might not be until either later today or maybe tomorrow. So I'm sorry about that. I wanted to quickly recap what we did last time, which was we derived the transport equation for the Reynolds stress tensor. All right, and we did that by starting with our Navier-Stokes equation and subtracting off the mean Reynolds, the mean version of the Navier-Stokes equation. And then we essentially multiplied that whole thing by the velocity fluctuation. And then we made use of the idea that repeated indices can be reversed. And then we added those two things together to finally arrive at a transport equation for the Reynolds stress tensor. Okay, so this is the kind of 9-equation system of equations for the transport of the Reynolds stresses. So this is our transport equation for the Reynolds stress tensor. Since, if you remember from before, that turbulence closure that we were looking at, we needed a transport equation for just the TKE. Which is the variable k, and that is 1/2 times the trace of the Reynolds stress. Okay, so what I'm going to do is, in order to get that equation, I will take the equation above, set k equal to I, and I'm going to just call them both m. Okay, and then multiply through by 1/2. Okay, so let's do that now. So this first term, I have ddt of um prime plus uj partial xj um prime is equal to 1 over rho prime partial p prime partial xi plus, oh, I'm sorry, partial xm. The i's are m's. Plus prime partial p prime partial xm. All right, so we'll notice that this is 2 times that quantity because they are the same. And then we have minus partial xj quantity m prime uj prime um prime
Sorry,
Minus.
did you mean to put the average term in the first term in the like brackets, like the average bracket around the partial p, partial xm as well, not just around the
Oh,
um prime?
yes, thank you.
Okay.
I got ahead of myself, apparently. That is a very different thing. All right, thank you. Okay, and then I also have minus the viscosity, partial xj, prime, prime, close those brackets, minus 2 times the viscosity, partial prime, partial xj, partial prime, partial xj. Okay. And then I also have minus prime, prime, partial uxj, minus prime, prime, partial ui, partial xj. Oops, sorry, that ui is um. All right. Okay. That should be okay. Okay, so we are going to make a couple of observations here. So these terms are the same. So I pick up a 2 out front for these. And then these terms are also the same. So I can combine them. Let's see. And then I think everything else stays as it is. Okay, so I'm going to just rewrite this, combining those two terms and then multiply by the 1/2. All right, so I have partial t of 1/2 prime plus uj partial xj of 1/2 prime, which is equal to minus 1 over rho prime partial p prime partial xm minus partial xj 1/2 prime prime minus 1/2 nu. Sorry, I want to order that differently. Nu times partial xj of 1/2 prime minus nu partial prime partial xj partial prime partial xj, and then minus prime uj prime partial partial xj. Okay. And now we see that we have our TKE that shows up in a whole bunch of places. So everything in blue is just K. And that's it. Okay, so this is K, this is K, and then this is K. So our final equation here is um partial K partial T plus UJ partial K partial XJ, which let me just move this down so I can make a small note about that. So this is just the material derivative of TKE by definition. And it is equal to minus 1 over rho prime partial p prime partial xm minus, I'm going to separate out these two terms. So I have minus 1/2 partial xj prime uj prime prime plus 1/2. Wait, did I screw up a sign somewhere? I think this sign on new is supposed to be positive. Hang on. Yes. Yes. Okay, so I think. Hang on, just double checking here. Yeah, it is positive. Okay, great. So this is new times partial xj of k minus new of partial prime partial xj partial prime partial xj. And then, hang on, I'm going to try and move this over so I can get it all on one line. Maybe not. Okay. And then last but not least, we have minus prime uj prime partial partial xj. Okay, so a couple things to note here. We have repeated indices. Hang on a second. I did make a mistake. This is supposed to be a Laplacian. I knew there was something wrong with that term. Hang on a second. Let me work myself backwards and figure out if I can find out what happened here. Ah, yes. Okay. So I someplace at some point I dropped this second derivative. So let me just make sure that it comes back. All right. And then here, that should be this here. And then there. Okay. So I was trying to say that in all of these terms, all of our indices are repeated, meaning this is a scalar equation. And there's physical interpretation for each of these terms. And so I'm going to go through that now. So this first term, of course, is just the local time, the local rate of change of TKE with respect to time. Our second term here,
Oh, sorry.
very echoey. Okay, our second term here, this is our advection of TKE. So you can think of this as like the TKE being carried along with the flow, the mean flow. Our next term is our diffusion of TKE due to pressure. So sometimes this is called pressure diffusion. Okay. Um, this next term with the triple prime in it is our turbulent transport of TKE. Sometimes this is given like a scripty T symbol, occasionally. So this is an important term that people tend to talk about a lot. That's why it gets its own special symbol. Um, this, let me find another color. I need lots of colors for this one. This term, so we have viscosity in here and then the Laplacian of the TKE. So this one is called the molecular viscous transport of TKE. Um, so that one looks very similar, like form-wise, to the viscous diffusion term in Navier-Stokes. The next viscous term here is our viscous dissipation of TKE. So this one here is viscous dissipation of TKE. So this one is generally given the symbol epsilon with a subscript K. That's another kind of notable one. And then the last term that we have here is also an important one. So I will give it the color purple. All right, and this guy is our production of TKE. And it is often given the symbol P, like a scripty P, which is hard to do with handwriting. Okay, so these are kind of the physical interpretation of all of these terms in this transport equation. Keep in mind that this we developed entirely from Navier-Stokes, so we don't have any assumptions or models in here outside of assuming that we were doing incompressible Newtonian flow. Okay, so let me make a note of that. So the only assumptions or restrictions that we've made are incompressibility, Newtonian fluid, and then we also neglected the body force. That we had in Navier-Stokes back when we, derived Navier-Stokes earlier this semester. Okay, so if you were to want to generalize this and say, okay, I'm going to generalize this for a flow that could be compressible or a flow that is perhaps non-Newtonian, you would follow the exact same process, but you would need to treat density and viscosity as non-constant in those cases. So you would end up with averages that include both viscosity and density, for example, and their fluctuations. So if you wanted to attain a completely general expression, you would treat density and viscosity as non-constant. And what would happen is that this would yield more terms, of course, that involve density fluctuations and viscosity fluctuations, for example, among other things, depending on especially your model for viscosity. Okay, I also wanted to make a comment about the viscous dissipation term. So a brief aside about dissipation. Okay, so we have that epsilon k is our viscosity times the gradient of the velocity fluctuations double contracted with itself. Okay. So if you remember back when we introduced turbulence as a topic, turbulence exists on different scales, right? Both in time and length. Or I guess space, I guess I should say. For computations that are fully resolved, in other words, computations that don't require any turbulence modeling. So if you wanted to just solve the conservation of mass and momentum equations in a discretized sense for a turbulent flow, that's entirely possible, but you need to make sure that your grid size is small enough and your time step is small enough. And to do that, we need to resolve the smallest scales. All right, so we're going to have to be careful about choosing our grid spacing size and our time step size. Such that it's on the order of the smallest spatial scale and the smallest time scale. All right, so these are called the Kolmogorov length scale. Which I think I already mentioned earlier, but I'm just reminding you. And then the time scale is the Taylor microscale. Okay, and those are defined as the following. So our Kolmogorov length scale is given the symbol eta, and it is equal to the viscosity cubed over the viscous dissipation to the 1/4. And then our microscale is given the symbol tau sub eta. I guess I should also mention that this is sometimes also known as the Kolmogorov timescale. And it is defined as the square root of the viscosity over dissipation. Okay. Um, now, couple of things to comment on here. This might all feel well and good, but if you think about it from the standpoint of actually running a simulation, hopefully you are thinking, well, wait a second. How in the world am I going to know what epsilon k is ahead of time? And the answer is you don't.
Do not
So,
know epsilon a priori, right?
what?
I said we don't know epsilon a priori.
Nope. Um, so, I will make a note about this.
Are you
So,
proud of me? I didn't ruin the surprise this time.
thank you. So, one of the key points here is that we can't know epsilon k ahead of time or a priori. Because we don't know gradients of fluctuations. Of velocity yet. Until we've run a simulation. Okay, so the question might be, well, how do you do anything then? And the answer is the following. There are, hang on, let me find it. I thought I had it pulled up here. So there are some correlations that you can use. That will get you started. And actually, I'm going to move this over because I have more to say about that. I'm going to put that here. Yes. Okay, great. Okay. All right. So what do we do? So to start a simulation, when you're setting up a simulation, we can use some scaling laws. We have a couple of options, actually. So we can use scaling laws to predict epsilon k. Or eta. And generally, we know that eta is approximately equal to L times the Reynolds number to the minus 3/4, where this L is an integral length scale. Or the largest eddy. Eddy diameter. Okay. So that being said, we can also, so that's one choice. The other thing that we could do is we can consult the scientific literature. To find eta or epsilon k from similar studies or experiments. But essentially what the process should be is you will use a scaling law or some previous information to inform a starting grid size. So the strategy, use scaling laws or prior studies to inform a starting grid size. So this is your first step. You're going to run your simulation at that grid size. Once you run your simulation, now you have access to what the actual dissipation is. So you're going to compute epsilon k from the simulation. Then you are going to compute the actual Kolmogorov length scale and compare it with your grid spacing. If your Kolmogorov length scale is smaller than delta x, so this is not very exact, but I'll just note we want delta x on the same order as eta. So what I mean by that is same order of magnitude. So if you have delta x is equal to 3 eta, that's generally okay. If you have delta x is equal to 10 eta, beginning to approach not okay. So generally anything higher than the same order of magnitude is going to be under-resolved. I understand that that's not an exact science here, so it kind of depends on what you are after. Ideally, your grid spacing would be essentially equal to eta. But typically, a well-resolved DNS, which I think I didn't write that down. So fully resolved computations are called direct numerical simulation. Or DNS, which hopefully you've heard of before. So yeah, so generally we would like to have our grid spacing kind of on par with Ada. I think in the literature, usually around 3 times Ada or under is pretty much well accepted practice. Once it gets quite a bit bigger than that, then it would be considered under resolved. Yes.
One quick question about the Taylor timescale.
Yes.
So would it ever be a case where the CFL wouldn't govern that? So like you have your Kolmogorov scale roughly at the same order of magnitude as the grid spacing, but your CFL is fine, but you under resolve the temporal aspect of it?
So that's a good question. So for those of you who don't know, CFL is let me write it down. So CFL number is the Quran. What's the F? Hang on. I forget. I always forget what the F is.
Yeah, I always remember the C and the L. I always forget
Yeah,
the
me
F.
too. Fredericks.
Louis.
Yeah. Fredericks. Louis number. So it's usually called C or CFL. And it is defined as the bulk velocity times the time step divided by the grid spacing. So for stability of a numerical solver, C should be less than or equal to 1. And now Lee's question was, I think I'm restating, can you specify delta X using the Kolmogorov length scale and then use the CFL to specify the time step size? And the answer is maybe. But the difference is that there's kind of 2 conditions that we are trying to impose. CFL is focused on numerical stability. It has nothing to do with correctness, technically, right? It just means that the numerics are stable. Whereas specifying that the Taylor time scale and the Kolmogorov length scale are small enough, that's ensuring that we're capturing all the physics. So those 2 don't necessarily need to be connected to one another. Does that make sense?
I just didn't know if it was like a happy accident that based off of all of the different uh, dimensional analysis that things lined up. So at that point, it doesn't diverge, but it's also potentially not right, I guess.
Right. Yeah. So you could certainly have a simulation that is numerically very stable and well behaved, but deeply under resolved and not capturing flow physics. So a good example of this would be if you are looking at flow past a cylinder, and your grid size is too coarse, you're not going to get the vortex shedding behavior, for example. And that is because you're not looking at the small enough scales that are where that instability is basically originating from. So your simulation numerically could be completely fine on the up and up, CFL numbers happy as a clam, but you're not actually simulating what you want. Does that make sense?
Thank you.
Sure. Let me write that down for posterity. 1 second. So we must ensure numerical stability and proper resolution both, oh, you're gonna love this, Lee. Both CFL less than 1 and delta X on the order of eta and delta T on the order of tau eta are necessary but alone not sufficient.
Very nice using the math terms.
I love it.
Yeah, I think what triggered that was like thinking back to the Ridley Bernard stuff for the ASME conference last year.
Mhm.
That I kind of just let things develop, made sure the Kolmogorov length scale was fine, and then just like I set a low enough time scale that I knew the CFL was going to cooperate. But then, as some of the turbulence developed, as some of the convection developed,
Yep.
it did touch a CFL of 1, and it had to decrease the time step. But I never really checked to make sure that the time
Oh,
step
that the
was
time.
sufficiently small. Yeah,
Hmm.
exactly. Because like I kind of just leave it to its own devices, and it'll adjust it accordingly in order to keep the CFL under check. But I guess double check to make sure that the Taylor time scale is also decent. Is yeah.
Yeah, I think typically, um, this is a little bit of a hand wavy statement that I'm going to make. But typically, if you are resolving the Kolmogorov length scale sufficiently, and then you're using CFL as a constraint for your time step, generally you should be pretty okay. But it is good to check just in case, especially if you are looking at like very high Reynolds number flows. So, um, both
So I
your
guess
as Reynolds number goes up, obviously. So if you look at where did I put it? So this relationship, like the Kolmogorov length scale, is going to scale with the Reynolds number. Um, so it gets, and that is why it is um, even more computationally expensive and becomes impossible to do direct numerical simulation of very, very high Reynolds number flows. Which actually, you know what? Let me check. Um, what is the highest Reynolds? So this is like a metric that um, tends to move with um, with computational abilities. Ugh, hang on, I can't. There's a plot of the Reynolds number that we've been able to do over time. Hang on. Let me see if I can find it. If I can't find it, I'll try to find it for next time. Let's see.
I think it was just in the media that NASA's been doing some like insanely high pure DNS simulations for some of their rocket research at like above supersonic, like very very above supersonic.
Oh, really?
Yeah,
Huh. Okay. Yeah, I can't find the figure that I'm looking for, but like it basically tracks our ability to do high Reynolds number simulations tends to scale with our computational abilities over time, if that makes sense. So, yes. Okay. One other thing I wanted to mention is when we do our computation of the dissipation from a simulation. So computing epsilon k from a simulation. All right, so epsilon k is equal to viscosity times the mean of the gradient of the velocity fluctuations double contracted with itself. All right, so this means that we essentially have a double summation here. So we have m going from 1 to 3, and then we also have k going from 1 to 3 of new average partial prime partial x k prime k, and then partial prime partial x k, right? Okay, so this is going to be equal to 9 terms here. So we have I'm gonna let u1 equal u, u2 equal v, and u3 equal w, and then x1 is going to be x, x2 is y, and x3 is z. Okay, just for writing less subscripts, I guess. So we're going to have this plus this plus this. So we have the fluctuations in all 3 dimensions with respect to x, and then that same thing, but now the derivatives with respect to y. Oh my goodness. Sorry, my pattern recognition ability is failing me today. There we go. All right. So you have all of that that needs to be sorted out. Okay, and then keep in mind, so bearing in mind that ui prime is equal to ui minus the mean, right? Okay, so I'm just going to show this for one of these. So we're going to look at this term first, this first term. So we can take, since this is a summation inside of the average, we can move the average over each of those terms that are being summed together, right? So for partial u prime partial x, partial u prime partial x, I can substitute in that this is partial u minus mean of u partial x times partial u mean of u partial x. Okay, which is partial u partial x minus partial mean u partial x times partial u partial x minus partial mean u partial x. And then I'm going to multiply that all through. So I have partial u partial x, partial u partial x, minus 2 times partial u partial x, partial mean u partial x, plus partial mean u partial x, partial mean u partial x. Okay, so this is the mean of the x gradient of u multiplied with itself minus 2 times the mean of partial u partial x partial mean u partial x plus the mean of partial u partial x squared, because I'm running out of room there. Never mind. That's sloppy. Hang on. I'll move it. Okay, plus the mean of partial u partial x, partial u partial x. All right, if you recall, when we have the mean of a mean, it's just the mean. Okay, so that means this is minus 2 partial u partial x, partial u partial x, and that is the same type of term as the second one. So this just is the average of the gradient of velocity squared minus the square of the mean velocity gradient. Okay, so I did this exercise to show you kind of strategically how we would post-process data in computations. It is very computationally expensive to calculate the fluctuations, especially at runtime, because your mean is always changing, right? So you have to kind of do this in a post-mortem state. So instead of calculating the velocity fluctuations or their gradients in the code, because this would involve essentially running over the whole time, getting the mean velocity, and then going back and post-processing and going through all of those time steps, subtracting off the mean, and then doing gradients of those fluctuations. That's very computationally expensive. We'd rather not do that. We will use then, we can collect partial u partial x, partial u partial x, and the average velocity to assemble the dissipation term. Now, obviously, I've only shown you like the 1-1 component of that. So you would have to do this sort of thing, but for all of those components. Another thing to mention is that this, if you recall, is the trace of our original Reynolds stress transport equation. So the viscous dissipation of TKE, or of the Reynolds stress tensor, the full tensor is going to actually involve mixed derivatives too. So the off diagonals will have the, like partial u prime partial x times partial v prime partial y, for example. But those are the off diagonal terms. Does this make sense? Okay, cool. So let's go back and remember what we were trying to do. So we now have a transport equation for the turbulent kinetic energy. So if you remember, we had a model that involved TKE. So our turbulent viscosity involved K. So I'm just gonna rewrite this so that we can remember. Our model for our turbulent viscosity depended on K. All right, so we had that mu T was equal to some constant coefficient, density times the length scale times mean K to the 1/2. All right, so we now have a transport equation. Have a transport equation for K, but it has a problem. Does anybody know what the problem is? I'll go back to the equation. So our problem with this equation is we have several more unclosed terms, which is problematic. Okay. And I will highlight so a lot of turbulence modeling is kind of like a game of whack-a-mole. So every time you develop a transport equation for the next turbulent quantity, you will proliferate more terms that you need models for. Okay. And this is just the nature of kind of the Reynolds decomposition and expansion that we do. Yeah. So if we consider our transport equation, now anything that is in terms of our quantities of interest, so anything that's in terms of a mean velocity, a mean pressure, and now K, that's fine. We're solving for those things, so those are considered closed. They don't need a model. Anything that's not does require a model. All right. So I'm going to rewrite this equation a little bit differently. So I'm going to use the material derivative just to reduce the left-hand side a little bit. And then I'm going to lump my divergence terms. All right, so we have that triple one, and then we also have the mean of rho, I'm sorry, P prime UMP prime. Okay, and then we had nu times UM prime U J prime partial UM partial XJ, and then minus nu times our viscous dissipation. Okay, so the unclosed terms, I'm going to highlight in orange. This guy, we do not know what that is. This guy, we don't know what that is. This guy, and this guy. Um, hang on a second. Okay, so I think we will end here for now, and we will pick this up next time from here, and we'll talk about what happens next in terms of how to address this. But there will be more modeling involved. Are there any questions?